periodic table.
But before that, what is the periodic table?
The periodic table, also known as the periodic table of elements, is an ordered arrangement of chemical elements into rows and columns. It is an icon of chemistry and is widely used in physics and other sciences.
Who made it then?
It all started with Antoine Lavoisier in 1789. He tried grouping the elements as metals and non-metals. 40 years later, German physicist Johann Wolfgang Daubrunner observed similarities in physical and chemical properties of certain elements. He arranged them in groups of 3 in increasing order of atomic weight and called them triads. Observing that some properties of the middle element, such as atomic weight and density, approximated the average value of these properties in the 2 in each triad.
Correct! After that, British chemist John Newlands was the first to arrange the elements into a periodic table with increasing order of atomic masses. He found that every 8 elements had similar properties and called this the law of opposites. He arranged the elements in 8 groups but left no gaps for undiscovered elements. 5 years later, in 1869, Russian chemist Dmitry Mendeleev created the framework that became the modern periodic table according to their atomic weight. If he found that they did not fit in the group, he would rearrange them. Mendeleev predicted that the properties of some undiscovered elements and gave them names. For example, aluminum, for an element with properties similar to aluminum, but it was later discovered as gallium.
And what after that?
German chemist Lothar Meyer produced a version of the periodic table similar to Mendeleev's in 1870. He left gaps for undiscovered elements but never predicted their properties. The Royal Society of London awarded the Davy Medal in 1882 to both Mendeleev and Meyer. The later discovery of elements predicted by Mendeleev, including gallium, scandium, and germanium, verified his predictions, and his periodic table won universal recognition. In 1955, the 101st element was named Mendeleevian in his honor.
Wait, hold on. I remember an element similar to his name. What was it?
Spot on! In 1955, the 101st element was named Mendeleevium in his honor.
Is that all of what happened for us to discover the modern periodic table we are using now?
Not yet. The concept of subatomic particles did not exist in the 19th century. In 1913, English physicist Henry Moseley used X-rays to measure the wavelengths of elements and correlated these measurements to their atomic numbers. He then rearranged the elements in the periodic table on the basis of atomic numbers. This helped explain disparities in earlier versions that had used atomic masses.
Also, in the periodic table, the horizontal rows are called periods, with the metals in the extreme left and non-metals on the right. The vertical columns, called groups, consist of elements with similar chemical properties. The periodic table provides information about the atomic structure of elements and the chemical similarities or dissimilarities between them. Scientists use the table to study chemicals and design experiments. It is used to develop chemicals used in the pharmaceutical and cosmetics industries and batteries used in technological devices.
Well, that was one hefty and very long process of researching about elements. And to think that the possibility exists that new elements will continue to be added at higher atomic numbers than those known is very interesting.
Hold on, what about periodic trends?
Periodic trends include electronegativity, ionization energy, electron affinity, atomic radius, melting point, and metallic character. Periodic trends arising from the arrangement of the periodic table provide chemists with an invaluable tool to quickly predict an element's properties. These trends exist because of similar atomic structure of the elements within their respective group families or periods, and because of the periodic nature of the elements.
First, electronegativity can be understood as a chemical property describing an atom's ability to attract and bind with electrons. Because electronegativity is a qualitative property, there is no standard method for calculating electronegativity. Electronegativity measures an atom's tendency to attract and form bonds with electrons. This property exists due to electrons' configuration of atoms. The more inclined of an atom is to gain electrons, the more likely that the atom will pull electrons towards itself.
Next, ionization energy is the energy to remove an electron from a neutral atom in its gaseous phase. Conceptually, ionization energy is the opposite of electronegativity. The lower this energy is, the more readily the atom becomes a cation. Therefore, the higher this energy is, the more unlikely it is the atom becomes a cation. Ionization energy increases from left to right in the periodic table. Electron affinity trends. As the name suggests, electron affinity is the ability of an atom to accept an electron. Unlike electronegativity, electron affinity is a quantitative measurement of the energy change that occurs when an electron is added to a neutral gas atom. The more negative the electron affinity value, the higher an atom's affinity for electrons.
Next, the atomic radius is 1/2 the distance between the nuclei of two atoms. However, this idea is complicated by the fact that not all atoms are normally bound together in the same way. Atomic size gradually decreases from left to right across a period of elements. This because within a period or family of elements, all electrons are added to the same shell. However, at the same time, protons are being added to the new nucleus, making it more positively charged.
Lastly, the metallic character of an element can be defined as how readily an atom can lose an electron. From right to left across a period, metallic character increases because of the attraction between valence electrons and the nucleus is weaker, enabling an easier loss of electrons. Metallic characters increases as you move down the group because the atomic size is increasing. When the atomic size increases, the outer shells are farther away. The principal quantum number increases and the average electron density moves farther from the nucleus. The electrons of the valence shells have less attraction to the nucleus, and as a result, can lose electrons more readily. This causes an increase in metallic character.
Melting point trends. The melting point trend is the amount of energy required to break a bond to change the solid phase of a substance to a liquid. Generally, the stronger the band between the atoms of an element, the more energy required to break that bond. Because temperature is directly proportional to energy, a high bond dissociation energy correlates to a high temperature.
Do you know the history of the periodic table and the periodic trends now?
Yes, although it was a lot. I found out the periodic table can be used to quickly refer to information about an element like atomic mass and chemical symbols. The periodic table's arrangement also allows scientists to discern trends in element properties, including electronegativity, ionization energy, and atomic radius.